Hello, ladies and gentlemen. So today I will be speaking about my article that I've submitted for this conference. It's a joint work between me and Mr. Michel Broniatowski. The title of this work, as you can see, it's Generalized EM Algorithms for Minimum Divergence Estimation. And to start, I will be starting with the title, since there are many terms which need to be explained. So there is the EM algorithm, there is proximal point algorithms, divergences, and in a second part is the application, which is mixture models. First, I'll start with divergences. So divergences, they are measures of discrepancy. They have some meaning of a distance, but mathematically they are not distances because they lack sometimes they lack the symmetry, and sometimes they lack the triangular inequality. How do you define a divergence? And for me, I will be interested in pi divergences. So I start by picking a non-negative convex function phi, and then for two probability measures, Q and P, with Q absolutely continuous with respect to P, I calculate this quantity, an integral quantity. A main property of phi divergences is that when P and Q are equal, then the phi divergence between these two measures is equal to 0. And what's important to us is the inverse, which means if the quantity, the phi divergence equals 0, I need that P and Q to be equal. And for this to happen, I need to suppose that function phi is strictly convex. Many standard phi divergences belong to this family of divergences, such as the Kullback-Leibler divergence, the modified Kullback-Leibler divergence, Pearson's chi-square, the Hellinger distance, and others for a specific choice of function phi. All these phi divergences belong to the well-known family, the well-known class of functions, which is called the Cressy-Reed class of functions. The question is, why use phi divergences? And in fact, a very interesting property is that they are robust against outliers and against misspecification, which means that if the model does not contain the true distribution, but provided that the true distribution is not very far from it, then the phi divergence can be robust, and we get estimators not very far from the true ones. Secondly, proximal point algorithms. What are these? Proximal point algorithms, they are optimization algorithms. So the general form, it's an iterative algorithm which can be written as follows. We take the objective function which we need to optimize to calculate its infimum, for example. We add a regularization term, P, which may be a distance or any distance-like function. And the main condition on P is that it needs to be non-negative and verifies Px equals to 0. And we insert a sequence of numbers, beta k, which needs to be non-negative. And in general, it goes to 0. For us and for my work, the sequence beta k will be constant and equals to 1. But that does not change anything about the convergence of the algorithm. The beginning of proximal point algorithms, they are not, let's say, very, very recent. The beginning was with Martinet in 1963, and his choice in his paper was the quadratic distance between x and xk. Why use proximal algorithms? What do we gain? in fact, there were many authors who tried to investigate proximal algorithms. And I can cite two main properties of proximal point algorithms, which are, the first one is that we get a better convergence speed. And there's the work of Stephen Chrétien and Hero in 1998, who have proposed a variant of the EM algorithm based on proximal point algorithms and got a superlinear speed, a better speed, convergence speed than the convergence speed of the EM algorithm. Secondly, proximal point algorithms can help us to avoid some of the saddle points. They do not ensure avoiding all the saddle points, otherwise we would gain linear omega. So this is what about proximal point algorithms. Thirdly, I'll be talking about the EM algorithm. The EM algorithm is a well-known algorithm which was introduced by Dempster and al. In 1977. It concerns the estimation of parameters in the context of unobserved data, which means we have a vector of observations, which is y, and on the other hand, we have unknown labels. It's the case when we do clustering. And what we want to calculate is the vector of parameters, which defines the model over the observation. The idea behind the EM algorithm is that we try to maximize the expectation of the logarithm of the complete likelihood. What is the complete likelihood? It's just that we use the joint density of the observed and the unobserved data together, provided the observation and the previous vector of parameters. A simple calculation can give us that the EM algorithm, this line, can be rewritten as a proximal point algorithm, which is where we have the log likelihood as an objective function, and we have a second part which is the a distance-like function, which resembles to a Kullback-Leibler distance. It does not matter for the time being. What interests us is that this writing permits us to conclude that the EM algorithm tries to maximize the log likelihood, since this term can be proved to be non-negative and equal to 0 whenever phi is equal to phi k. Phi will disappear. As we write the EM algorithm as a proximal point algorithm, there was a generalization proposed by Paul Singh in 2004, who tried to generalize this line by replacing the logarithm function here by any, let's say, concave function. But if we take into account the minus, then we are adding here a convex function psi, which needs to be a non-negative function here. So the generalization of Singh stays in the same sense as the EM algorithm, which means that we always have the maximization of the likelihood. And when we work with the likelihood estimators, the maximum likelihood estimator is not robust. So the generalization of Singh does not ensure a robust estimator. And what we need to do is to try to generalize this formula into a robust one, a formula which gives us estimators which are robust. In order to do this, I need to create a link. Well, I will not create it, it's always there. A link between the log likelihood and a phi divergence. And in order to do this, I will go back to phi divergences. A phi divergence, it's a quantity which calculates, let's say, a distance between a model p phi and the true distribution of the data. However, the true distribution of the data is unknown during the training, during estimation phase. So we need to estimate it. And what I propose to use is two formula based on functional duality. And these formula are called the dual representation of phi divergences, which was, they were introduced by Broniatowski and Lees and Vajda independently in 2006. The resulting estimate of the phi divergence is a supramal formula, which is written here. The problem with this formula is that it gives a good estimators when we are under the model. However, when we are not under the model, there is a problem, and we do not get robust estimator. For this, I have recently proposed a modification of this formula in order to make it robust. And in the same time, I can get rid of the supramal formula, which simplifies our life in practice. A main property for these two dual formula estimators is that as we choose the function phi t to be minus log t plus t minus 1, we get that the argument of the infimum of the estimated divergence coincides with the maximum likelihood 1. So this is the link which I need to exploit and use in order to introduce my algorithm. So going back to Tsing's generalization, which is written as the difference between two terms, the double likelihood and a distant-like function. I use the link between the maximum likelihood and phi divergences for the function phi KLM, as I noted here, for modified Kullback-Leibler, minus log t plus t minus 1. So this line can simply be written as a difference between two terms. The first is the estimated divergence of phi divergence, and the second one is the distant-like function. So we can remove the minus and the n in order to get the final line. Now, let's say a natural generalization for this formula is to replace function phi by any non-negative convex function, or let's say strictly convex functions, it would be better, in order to get the final line here, which is what I propose as a new algorithm, which should give robust estimators. A brief summary of what I've done till now. So I've started with the EM algorithm and its proximal, let's say, formula, likelihood, and a distant-like function. The generalization of Tsing, which transformed this term into this one with any non-negative convex function psi. After that, I have replaced the log likelihood and did what is necessary to obtain a phi divergence and a distant-like function. And this is what I had proposed as an algorithm. What I have wished for was to separate this line of optimization into two sub-optimizations in the same way the EM algorithm does for mixture models. For mixture models, the EM algorithm we apply the optimization for the proportions apart and for the parameters defining each class apart. However, it was a very difficult task, and I couldn't get to it. The only thing I could do was a directional optimization of this line. But I do not present it here for the of space and time. So now that the algorithm is presented, what does it ensure? We need that the algorithm converge and towards what? So the first property is that the objective function, which is the estimated phi divergence, is ensured to decrease under not very difficult, let's say, assumptions. We demand just lower semi-continuity for the objective function, the estimated phi divergence with respect to phi, and the distant-like function also. There is another, let's say, not very clear assumption where we take a set phi 0, which is the set of all vectors for which the objective function, the estimated divergence, has a value less than the initial one. Phi 0 here is the initial point of my algorithm. So I take just the space which ensures a decrease of the algorithm. So I suppose that this set is a compact set. This assumption can be replaced by a compactness assumption over the parameter space. So with these assumptions, I get the interesting property that the phi divergence decrease over the sequence of points phi k. The second property is the convergence towards stationary points of the objective function, which is the estimated phi divergence. And for this to happen, I add an assumption of C1, that the distant line function to be C1 function. For the objective function, if it's C1, then everything is okay. If it's not, then what we can prove that is that it is a generalized stationary point, which means that the 0 belongs to the subgradient of the objective function calculated at a limit point of the sequence. In the second part, in some applications, it's important to know some information about the sequence phi k. Will it converge, and towards what? For this to happen, more assumptions are needed. So continuity, compactness of phi 0, they are the same. However, we need to add a, let's say, identification property of the distant line function. Is that it equals 0 if and only if the two coordinates are equal. The problem is this assumption does not hold for mixture models. If all these assumptions are verified, then the consecutive distance in the sequence will converge to 0. Phi k plus 1 minus phi k will converge to 0. And if we add more assumptions, such as, let's say, strict convexity in the neighborhood of a limit point of the objective function, then we can ensure the convergence of the whole sequence and towards a local minimum this time. About my simulations, I'll try to just do some simple simulations. So I've chosen the Gaussian mixture and a Weibull mixture, 2 components. So a mixture model is written as we take 2 probability densities and we mix them with a lambda in 0, 1. For my the practical part, I have 100 observation. For the phi divergence, I've chosen the Hellinger one. And for the distant line function, I've chosen the chi-square, the psi t, which corresponds to the chi-square. Above the error criteria, I calculate the total variation distance, which represents the maximum error when we calculate the probability of a Brownian set. The results, a big table, but what interests us is that the total variation distance. For the classical dual formula, which is not robust, we get the best result under the model with a total variation of 6%. When we are not under the model, my kernel-based formula gives the best one. This is for the Gaussian model. For the Weibull mixture, the same conclusion holds. Final conclusions. What I can say that, firstly, it works, which is important. Secondly, my kernel-based dual formula is a robust one. However, the classical one is not. Thirdly, the classical formula gives a very good estimation when we are under the model, and even compared to the EM algorithm. And there is just the fourth point is that the EM algorithm seemed to be very sensitive to initial points. However, the proximal algorithm was not. Thank you for your attention. What do you mean by generator? Sorry, I don't understand. What do you mean by the function phi? For the simulations, I've tried in the same class of phi divergences. I've tried the Nyman chi-square. Results were, let's say, the same, not very far. I did not try other phi divergences, and especially for divergences which, let's say, a divergence such as the Nyman chi-square divergence needs big attention in the practical parts, because integrals may not converge and such things. So I just considered the Hellinger and the Nyman chi-square. The Hellinger, my choice for the Hellinger was based on many results and articles which says that the Hellinger is efficient and robust in the same time, which is not verified for others. Yeah, and efficient in the same time. That's why I've chosen the Hellinger